Okay, we'll be starting in about 1 minute.
All right. Thanks, everybody, for joining us today. We've got a session with Greg McMillan on live process control. The topic is PID tuning for near integrating processes, or as Greg would say, how to reduce the tuning time for column and vessel temperature and pressure loops by 90%. This broadcast is being recorded and will be available for future viewing. And we'll be muting all but Greg's microphone, so I'd ask that you use the Q&A box to ask any questions that you have of Greg, and I'll be monitoring the Q&A box and I'll relay them to him verbally during the course of today's session. And we'd like these to be as interactive as possible, so as questions occur to you, fire away. With that, let me turn it over to Greg.
Thank you for joining us. This seminar is sponsored by Emerson, that's a local business partner in St. Louis, Xperia Tech, and Mina, who does process modeling. It was created by me and Jack Ehlers, who is a process control specialist at Monsanto, and it is based on using a process control lab, and that website was designed by Charlie Schleiser in St. Louis at CS Design Co. Well, this is me, and what I've learned over the course of my career. I've been putting on my website for the last 4 years, and there's like over 150 entries there, so check that out if you want to see what I have learned and want to share with people. Of course, I like to do top 10 lists, so here's my latest one. I just thought of this last week. It's top 10 keys to excellent life and loop performance. Number 10, maximize disturbance rejection, adaptation to changes, ignoring noise, exhibiting self-regulation, reaching targets faster, coordinating actions. Sometimes not all that coordinated. Try to be mentally, though. 4, minimizing oscillations. Effectively using feedback, even if you don't like it, and optimizing goals. And the number 1 key, minimizing dead time. That's both literally and figuratively important. So we're going to talk about near integrating processes, which is a slow self-regulating process, and when I mean slow, I mean it has a large process time constant. I do not mean that it has a very large dead time. And you can do an open loop test here, which is what we've shown. We've changed the controller output, and we're looking at the response of the controlled variable. Now, normally we think in terms of process variable, but that's in engineering units. What we see on trend charts as a process variable is in engineering units, and that's essential. But the controller algorithm, the PID algorithm, is working in %. So to make this distinction between process variable and what the PID algorithm is using as a controlled variable, I've switched to the nomenclature of CV. This is also the nomenclature nomenclature that's used in model predictive control. And the important thing is that the control variable is in percent and the controller output is in percent, whereas what you see in terms of a PID implementation in your process may have the controller output in engineering units, particularly if that controller output is going to a set point of another controller. So what we have here is an open loop response, which is the response to the change in controller output with the controller in manual. And so at this time here, we've made a change in controller output, and we've changed it on up to here. So we've got a delta CO. There is a period of essentially negligible response. There may be a tiny response, but it's kind of indistinguishable between noise. Once we get out of the noise band, at this point here, that signifies the end of the dead time. And so it's a pretty good way of getting, and pretty easy way of getting an estimate of the observed dead time. And we call it the process dead time in the literature, but it could be dead time due to the automation system. For example, it could be due to scan times and module execution times for fast loops. It could be due to measurement time constants, particularly if you have thermal wells on temperature loops. It could be due to pre-stroke dead times, control valves. It could be due to sample delays for analyzers. So this observed dead time comes from a lot of different sources, although in the literature it is called the process dead time. Then we start to see the response after the dead time, and if we reach about 63% of its final value at here, that signifies the end of the process time constant. So from the start of the end of the dead time to when it reaches 63% of its final value, we've got the process time constant. Then it eventually is going to line out. Now, I want to squeeze this all on here, and really this wouldn't line out until about 4 time constants. Here I've got it shown lining out at 2 time constants just to squeeze it on this page here. But really it's going to take a lot longer for it to line out. And so you, in the conventional way of doing a tuning test, or at least an open loop test, you would be waiting for it to reach steady state for the self-regulating process, and really it would take not only the dead time, but about 4 time constants for it to get pretty close to where it's going to end up at. And there's the key to the slowness of the test, and that even if you're not doing this open loop test and doing closed loop tests, say with auto tuners or adaptive controllers, they're going to be looking for a time to steady state as the time window that the tool should be looking at to identify the settings. And so it is going to, end up being a big time window, because if you have a large time constant, you end up having to wait 4 times that time constant plus the dead time to get to the steady state. Most temperature loops have a process time constant so much greater than the dead time that the response is a ramp in the allowable control error about the set point. In other words, if you have a temperature loop and you really want to keep it within a few degrees of set point, for say for column or vessel or reactor temperature control, and you were to make an open loop test, in that region of a few degrees about set point, it'll look like a ramp. And therefore, we term them near integrators. A true integrating response would be a ramp that would just continue on and really reach no steady state. But in a lot of interesting and important loops, like temperature and pressure on vessels and columns, that steady state is way out there, either in time, and in some pressure loops, it's beyond the operating region, allowable. So you never get to that steady state. The pressure never, say, on an increase gets high enough before you've exceeded the operating limit of, say, the column or the vessel. And so you never see the steady state. And what you see is a ramp. And this is kind of a very difficult process that would be in ear integrating, because it's showing that it has this additional time constants in here that cause some slowness here in the beginning that then gets into what would be the ramp phase that you would really be interested in. Most processes are not this exaggerated in terms of the other time constants causing this, and what you would see is more like a ramp starting right at the end of the dead time. So if you're familiar with Lambda tuning, then these equations here are familiar to you, but we'll just go over them briefly here. First of all, the self-regulating process gain, we're looking at the final change in the control variable in percent and dividing it by the change we made in the controller output in percent. We're using that process gain in an equation for the controller gain, and in the numerator is the integral time setting, and here is the process gain in the denominator. But then we have this other term here, which is shown here the way it was originally in lambda tuning, where we have a lambda factor times a time constant, and we add the dead time to it. Now, what's a little bit more convenient is, instead of using this lambda factor times the process time constant, is to just think of a lambda that is a closed loop time constant. And this closed loop time constant is really best visualized and utilized for setting the set point response. So this was really based on what would be the closed loop time constant if the controller wasn't automatic and you made a set point change. In other words, how long would it take to reach 63% of the set point change? One of the things about lambda tuning is that you simply set the integral time equal to the process time constant. We're going to use a near integrator gain approximation, and we're going to do that by trying to estimate the maximum ramp rate and then dividing that by the controller output. And we're going to do that very early in the response. And we'll see that in general that works out pretty well. So we take the maximum ramp rate near the beginning of the response, and we divide it by the controller output that we made. Changing controller output, and we end up with an integrating process gain. Now, if you want to relate that back to what would be an equivalent model in terms of self-regulation response, you could say that is the self-regulating process gain and divided by the self-regulating process time constant, and we'll see how that can be useful later on. Now, one of the things about this, if you want to visualize it in terms of a process time constant, the equation can be solved for the process time constant by simply taking the process gain equal to 1.0. Or for more sophistications, you can take it as the average ratio of the controlled variable to the controller output, over a period of time that's representative of normal operation. The other thing that's not realized is that this tuning test doesn't need to be done with the controller in manual. It can be done with it in automatic for a set point change. If you have a high enough PID gain, the PI structure is a PI on error, DMPV, so that the key thing is, so you see a step change in the controller output from the proportional mode as you made that set point change. And since we're looking very early on in the response to measure the maximum ramp rate, hopefully the integral or reset action has not really had much of an effect. And in fact, if the interval time is much larger than the dead time, that is generally the case, and we're going to get a pretty good estimate for what the near integrating process gain is by doing this test with a controller and automatic. And in fact, it's been shown for bioreactors for temperature loop tuning that we got very accurate models from looking at this initial ramp rate for tests where set point changes were made with the controller and automatic. So we're going to look at simplifying the tuning now. We're not going to have a process time constant, so what we're going to do is go for maximum load or disturbance rejection by setting lambda equal to the dead time. So we're going to take lambda and we're going to substitute the observed dead time for that. And if we do that, plus we take into account this relationship here and this relationship here from lambda tuning, and substitute that into the equation from lambda tuning for the controller gain, we end up with a much simpler expression for the controller gain, where it is simply 1/2 the inverse of the product of the integrating process gain and observed dead time. And so if we measure this initial ramp rate very quickly, and we know, of course, the dead time right off the bat, we then can get a controller gain. And so how do we get the interval time? Since we're not going to wait to steady state so that we get an idea of what the process time constant is, what we can do is set the interval time equal to 4 times the overall or observed process dead time. And it turns out that these equations here are kind of universally been used in very different ways. There's a lot of different tuning methods, and they may change this factor here a little bit. This factor varies from 0.4 to 0.8, depending upon, actually from 0.3 to 1.0, depending upon the tuning method, your favorite tuning method. And this factor here may vary, you know, from say 1 to about 10. And depending upon your favorite tuning method and whether you're going for disturbance rejection and whether you're going for set point response. But basically they come down to very similar values, particularly when we're going for maximum disturbance rejection, if that's our goal. And if you go to the Ziegler-Nichols reaction curve method, and that's not to be confused with the Ziegler-Nichols ultimate oscillation method. Most people are aware of that, and boy, it's got a lot of bad press over the years because people don't want to oscillate their processes. And furthermore, it ended up with a response that was quarter amplitude damping. It was oscillatory. It was very hot, and not only was it oscillatory, but it wasn't very robust. And by robust, I mean that it was sensitive to changes in the process gain and the process dead time, process dynamics in general. The Ziegler-Nichols reaction curve method is not as well known, and it used an open loop response, and it was measuring effectively a ramp rate. However, it did it by constructing a tangent to the inflection point of the self-regulating response. So it needed to wait again till steady state for it to know that, okay, let's draw this tangent and let's get then the slope of this tangent and use that as the integrating process gain. Well, it turns out that these methods can be equivalent, and really what we're ending up with is the Ziegler-Nichols reaction curve controller gain, but about half as aggressive as it. And again, this is the idea of the Ziegler-Nichols going for quarter amplitude dampening. It was too oscillatory in general for people liking, and also it was maybe not robust enough. So simply we've effectively cut that gain in half by going through these substitutions, and we've retained, though, the relationship here that they proposed, that the reset time be equal to 4 times the observed dead time. Now, if you want a set point response that's smooth with minimal overshoot, then you could go with 10 times the observed dead time as your reset time. Okay, so how much time are we going to save? Well, the near integrating tuning test time takes about 3 dead times. And that you got to get past the first dead time to get a response, and then you want to get the maximum rate of change by observing the response over the next couple of dead times. Now, the self-regulating tuning test is the time to steady state, and that time to steady state, as I mentioned, is basically the observed dead time plus 4 times the process time constant. And in the numerator here, we have the near integrating tuning test time as being 3 times the observed dead time. So we've got this relationship here in terms of what fraction of the self-regulating tuning test time are we going to see in the tuning test time for a near integrator. If the process time constant is greater than 6 times the observed dead time, then we end up with a realization where it's only taken us 1/10 of the time required for a tuning test for a self-regulating process. In other words, we've reduced that time requirement by 90%. For our example today, we're going to use a process time constant of 100 seconds, and the observed dead time to pure dead times and small time constants is about 4 seconds. And we're going to see then that we can reduce the near integrate, by going near integrating, we can reduce the tuning test time by 97%. So we're less than 0.03 as a fraction of the tuning test time that we would have had for a self-regulating process, open loop response, or and I guess in a way that's what's setting what the tuners are looking for in terms of even closed loop responses. So let's go and look at our process control lab and see what we can identify in terms of ramp rates. But first we need to increase the process time constant to 100 seconds, and then with the set point at 10% and the controller and manual, we're going to increase the output by 40%. And that's going to take a while for it to respond again with this 100-second time constant. So while we give it time, we'll come back here to the seminar. So let's go and go to the process control lab. And we're going to be working with a single loop. And here we have it already at 10%. We'll throw the tuning details up there. And we're going to put the controller manual. Oops, and we need to change that primary process time constant. So let's go and do that. Click on any of those blocks, and then we click on the process tab. And the big time constant here for the primary process is lag 2. And I've got it for both increasing and decreasing direction, so I got to set it in both places. Okay. And we ought to bring up our trend chart. And everything's lined out here. We're going to highlight the primary loop process variable. And so we're going to see how it responds to this change in manual controller output. So here we're going to, whoops, this is the point. We're going to change the manual controller output by 40%. So we add 40 to 10 and we end up with 50. Now we see we got the change in controller output, and got real soon after that we got a change in the process variable, but that's partly because this trend chart time scale needs to be decreased, so we need to do that to get a much better idea of what's going on here. Okay, now we can see the dead time here. That wasn't apparent before. So now we made a change here, and there was a period of time where there was no response, and you can kind of zoom in on that, and it's pretty close to 4 seconds. Well, it's going to take a while for this to really reach steady state, because it is a slow process, and this is what you'd have to do for a conventional tuning test. So we'll go back to our seminar demo. I guess that's what you can do if you're doing conventional tuning tests. You can do multitasking, and you can go do something else while you're waiting for it to respond. I think there's a significant opportunity way beyond tuning, and that is how would you like a real-time simulator of your complete process? But you don't have the time to really spend identifying all those process models, particularly these really slow ones. Like, you can spend the time identifying these slow process time constants of the more important loops that you're interested in. You know, for flow, it's, no big deal, but again, the flow dynamics is something that you can quickly get at, and the process time constant there is so fast, is essentially a non-issue, or really doesn't get involved into what you're modeling that much. Anyway, so here we have an opportunity through these tests to develop process models, and we can develop just about any type of process model that you can think of, and we can end up with a process gain approximation, a steady-state process gain approximation, if that's what you want, by simply taking that average of the control variable divided by the average of the controller output over a period of time, and the subscript here is O for observed, or overall, or initial, or whatever, and just to distinguish that it is kind of an average value that you're starting with before you do the test. Then you can, like we say, solve for the process time constant, and it could be for a negative feedback time constant, or it could be for a positive feedback time constant. Now you have 4 different types of model. The one here that's most sophisticated is at the bottom. It's an ordinary differential equation, and it's going to be a combination of first principle model and experimental model, in that by identifying the near integrating process gain, we can then home in on some parameters that possibly we didn't know that much about. Now, we often know the area for heat transfer. We often know how much liquid, and if we, given the density, we know the mass that's in there, and the heat capacity is usually well defined for a lot of processed fluids. What we don't tend to know is the heat transfer coefficient, because it depends upon what the condition of the surface is, both in the vessel and also on the, say, the coolant side, and it depends upon velocity and operating conditions. And it's a complex function of a lot of different process variables. So here we could get a pretty good fix on it by solving for it once we know or have an experimental value for the integrating process gain. So we can then end up with the first principle experimental model as being model 1. Model 2, we're going to say, hey, let's model it as an integrating process here. So the case of I says, hey, this is our integrating process gain. That's what we're going to use. We could model it here. Number 3 is a self-regulating process. So we're going to take our estimate of the steady-state process gain and the steady-state process time constant. And we've got those values, like I say, from identifying the integrating process gain. Similarly, we can come at values for a runaway type of process, positive feedback type of process, and we can end up with estimates there of the process gain and the positive feedback process time constant, and that's what this little plus sign here is meant to designate, that we got a positive feedback process time constant. And that's going to be Deminar number 8. We're going to talk about runaway reactions and how do we tune and control them. So we start out with a controller output, and we subtract from that the controller output from the last scan or last execution. We've got a delta controller output. We send it through a dead time block where the delay is set equal to the observed dead time. And then we send it through one or more of these models, and we use a switch to decide which model we want to actually end up with as a delta C sub V. We then add the last value of the control variable from the last scan, and we end up with the predicted or simulated value of the control variable. And we're doing this in percent, but you could easily then convert it to engineering units. So, just kind of summarize, the observed dead time and the integrating gain are identified after changing controller output. It could be, a controller output going to a final control element, such as a valve or another loop, or it's changing a set point, or it could be any disturbance measurement. The identification of the integrator gain uses the fastest ramp rate over a short time period, say 2 dead time intervals, at the start of the process response. The models are not restricted to loops that can be used to identify this relationship, but we can do it between any variable that can be changed and any affected process variable that can be measured, so we can get a comprehensive plant-wide real-time simulator. The models are used for processes that are true integrating response or near integrating response, or, as we mentioned, even for runaway reactors. A special case. So we have these 4 types of models, and a patent disclosure was filed on March 1st. So let's see if we've reached steady state, and let's see then if we can estimate the dead time and the maximum ramp rate in the next 2 dead time intervals, and then we're going to divide that ramp rate by the change in controller output to get the near integrating process gain. Well, it looks like we finally have reached steady state, but we need to go back here at the start of the response. Whoops, went too far. So, we made a set point change of about 48 seconds, and we're starting to receive a response somewhere between 3 and 4 seconds afterwards, and normally there'd be some noise on here, so it is safer to take a little bit more as the dead time. That's the more conservative thing to do, and so that's what we will have here, 4-second dead time. And so where did that 4-second dead time come from? If we go back here to our process dynamics and we add up all the delays and additional time constants smaller than the largest, here we see we have a delay of 1 second, the primary process. We have a delay here of 1 second in the secondary process. And then we have a time constant, a very small time constant in the secondary process. If you add those all up, and this is the general rule of thumb for estimating the observed dead time, you add up all the pure delays and all the small time constants, that is your overall observed dead time. Now we're lucky in that we have a perfect control valve, and it's very fast and slewing rate, so it doesn't add any delay or any lag. And we have, in fact, the lags out here are also set to 0, and there's no delay associated with working through the stick slip or the dead band. So it really comes down to the process, and if we sum up all of the small lags there and delays, we end up with 4 seconds. So let's go another 4 seconds out and see how much the controller output has changed. And if we go to, let's see, we started at 48, 50, and went to 52. So if we add 4 seconds, we want to go to 56. And there we see we've got a change of a little over 1%. Let's go another 4 seconds, which means we'll go right to 28 minutes. And we're starting out at 11.04 here. Let's see if that's actually, let's say we started out here at 1098, and now we're going to go 4 seconds, and we're going to see where we end up with here. Okay. So we're now at 12.50, and I have a little spreadsheet here at and this would be 10.98, and this would be 12.5. And we end up then, given a dead time of 4 seconds and a change in controller output of 40%, we end up with an integrating process gain that is very close to 0.01% per second per percent change in controller outputs. Or if you cancel out the percents there, the units are 1/seconds. This gives us a controller gain of about 13. And based on the dead time for maximum load rejection, we're just multiplying that by 4, and so our PID reset time is 16. So we, at this period of time, like 16 seconds into the response, we have identified the dynamics enough to do tuning or to create a process model for a plant-wide real-time simulation. So let's go back to our Deminar and see what some previous calculations have given us, and we'll then look at what the tuning settings are from those previous calculations. Okay, from a test I had done yesterday, here we made a change, and well, as we were making the change, the process variable was not completely lined out. There's a little bit of fluctuation there, and so it is at 10.02. At the end of the dead time interval, which is 4 seconds later, again, I guess I didn't flag that, we started at 10:10, and then 4 seconds later we're still at 10.02, and we're at 10:14, 14 seconds after 10 minutes. here now, we're at 10.76 after another 4 seconds, so we're at 10 minutes, 18 seconds. And here we're at 12.34 at 22 seconds after. And so if we take our case here, process time constant 100 seconds, dead time 4 seconds, and for our purposes process gain is 1, and we use this very simple equation here for controller gain. We end up with a controller gain of 12.5, and you could say, oh well, I came up with 13.1 before, but really any sort of tuning calculation is only really accurate to one significant digit, or at most maybe sometimes 2. Really, if you get, within 25% due to changing conditions, you're realistically that's good because of process nonlinearities and non-idealities like control valve stick slip and backlash and all sorts of things that happen in the real world. So it's kind of funny when you get people, and this happens particularly for simulations, they're arguing over whether this is 12.5 or 13.1. I mean, and they're kind of missing the big picture. And then for the reset time for maximum load rejection, we're going to simply multiply the dead time by 4 and end up with 16 seconds. If we want to go with a smooth set point response, we're going to multiply it by 10 and end up with 40 seconds. Now, we could have used a whole other set of equations if we wanted to, but you probably saw enough equations today, and we'll keep that in reserve for our next seminar where we have a true integrating process. There's another set of equations. What's interesting is they reduce and give results very similar to the simpler set here for our situation. So, if you want more sophistication, you can do that. Okay, so now we're going to go back to our demo, and we're going to substitute, well, we did this already. We've got the integrating process gain, and we come up with controller gain. And so we now have a controller gain that we're going to put into the loop, and we're going to set the reset time at first equal to 10 times the dead time because we're going to see the set point response. We're going to match that set point to the process variable since we're now at 50%. Put the controller in auto. We're going to make a 10% set point change with the set point response tuning, and we're going to go from 50 to 60. Then we're going to set the reset time equal to 4 times the dead time, which is the tuning for the load response. We'll make another set point change, in this case from 60 back to 50. See the difference between the set point response tuning and the load response tuning. And then we'll finish up by making a 10% load disturbance. See how well it does with this maximum disturbance rejection tuning for loads. So let's go to our demo. And we're going to have to go forward so we can see what's happening now. Okay, so we're going to start out with set point response tuning. So we're going to set the interval or reset time 40 seconds. The controller gain is 12.5. So that's our new tuning. And we're going to change the set point to 50% to match it up with a process variable. If we had set point tracking PV, we wouldn't have to do this. We're going to put it in automatic. Okay. Now we're ready to see what kind of tuning or response we're going to get from this tuning. So we'll make the set point change to 60%. And notice we got quite a kick from the controller output. That's great for getting the set point faster. That's what you want for the startup of your continuous operations, or for your grade changes in continuous operations, and also for your batch operations. You want to get the set point quickly. And notice that there's very little overshoot. It's at set point, looks like it's kind of lined out. So let's put in the load response tuning, and that means setting the reset time equal to 4 times the process dead time, or 16 seconds. And now we're going to make a set point change in the opposite direction. And it's approaching set point pretty fast. Remember, these major time divisions here are 1 minute, and it's getting to set point G with in about a half a minute. But see, we got a little bit of an overshoot here, and it's not much. And gosh, you could say, well, what the heck? It doesn't matter. But if you really are concerned about overshoot, and some bioreactors they are, although I kind of doubt they're operating that close to the optimum, but if they were, this could be an issue maybe. The overshoot is about 0.7 degrees. Yeah. And here, going the other way, looks like maybe 0.08 degrees then is the next amplitude of the oscillation. Let's find out. So let's see how it does with a low disturbance, and we can do that by momentarily putting this controller in manual and increasing, say, the controller output by 10% to simulate a 10% load disturbance, and then throw it back in automatic right away and see how it does dealing with this load disturbance. We've decreased the time scale so much here. It's the trend recording doesn't look all that smooth. Let's see if we increase the time scale. Yeah, that looks a little bit better maybe. Well, the peak error here for that 10% load disturbance is pretty small. Gosh, it looks like it's about 0.73%, or well, and the starting value was a little bit above. So it's about 0.7% overshoot. So you can see it did a pretty good job. Now, if you concerned about the controller output, maybe that could bother you, but often the vessel temperature, particularly reaction temperature, column temperature, it's most important that that temperature be controlled at set point, and some gyrations there in the controller output, the coolant, or in the case of temperature control, the distillation column, the distillate flow, those short-term gyrations are not as big an issue as the tight temperature control. Remember, temperature is important often for composition. Literally in the column, it's an inference of the equilibrium, and therefore operating point there for the composition in the column. That's why they use, tray temperature or some packing temperature location point to essentially control the product composition. Well, in reactors too, the temperature is setting the reaction rate, which determines, the product, and therefore it's really controlling the product composition that's coming out of a reactor. So tight temperature control is very important for chemical reactors, biological reactors, columns, and crystallizers. A large variety of very important unit operations. So that's the demo. Go back to our slides.
All right, thank you very much, Greg. And I just added a question to the Q&A box, or put something in there to basically put the URL that you can cut and paste to a little one-question survey with a comment field where you can provide your feedback to today's podcast. Or to today's seminar. We really appreciate your feedback on that. Okay, our next session is scheduled for July 14th, same time, 10 a.m. Central or 1300 UTC, and the topic will be PID tuning for true integrating processes, and that's how to reduce batch cycle time for temperature and pressure loops by 25%. Also, as soon as we make the video of today's session and upload it to our site, we'll update modelingandcontrol.com, which is Greg's blog, and emersonprocessexperts.com, which is my blog, with links to the recorded version of it, so you can share that with others that you may know. And I guess with that, let me open up the floor to any questions. Use the Q&A box, and we'll be quiet here over the next minute or so, just waiting to see if any questions come in. So thanks a lot. All right, with that, thank you everybody for attending today's webinar. We'll see you at the next one.
Thank you.